All right, so that was regression and outliers. So now we'll do a few more tests that you might want to do. So one is tests of independence. So if you want to test that the proportions are the same in two different groups, you have a couple options. If you're dealing with small sample sizes, say less than 1,000, you can do a Fisher's exact test. Or if you're dealing with large sample sizes, like greater than 1,000, you can use a chi-squared test of independence. So the example that is listed here is that, let's say you have patients and they either were treated with a drug or placebo, and then some patients live and some patients die, and you can compute the probability that these two means are the same, or that these proportions are the same, not means, but proportions in the two groups using these tests. So I'll just go through this quickly. So the Fisher's exact test, you're going to give it a table, a 2x2 contingency table. So, and then it's going to give us an odds ratio and a p-value. And we're also going to supply whether we want to do a two-sided or a one-sided test. So we'll do a two-sided in this example. So in this example, we're going to look at whales and sharks in two different oceans. And in the Atlantic Ocean, we counted 8 whales and 2 sharks. And in the Indian Ocean, we counted 1 whale and 5 sharks. So it looks like these are different. But if we actually want to test this, we can do a Fisher's exact test to compute the odds ratio, which is just the test statistic. And the important thing here is the p-value. So with a commonly used alpha of 0.05, this p-value is significant. So it's the chance that we would observe a ratio either this imbalanced or more imbalanced by chance is about 3.5%. So that's a Fisher's exact test if you have a small enough. Nowadays with computers, you can compute higher things, but if you want to approximate this test, you can use also a chi-squared test. So in this case, it's going to give us a few more things. It's going to give us the chi-squared test statistic, a p-value, number of degrees of freedom, and the expected frequencies based on the computation. So here we can take that same data, which is quite a small number of counts. We wouldn't need to use a chi-squared test, but we can, and we can see that, again, we have a borderline significant p-value that we get. And then we also get, the nice thing is we get these expected proportions based on the computation. So that's some tests of independence. And then somewhat related to that is analysis of variance. So this is where you want to see if the means of two distributions are the same or not. So there's a few different ways we can do this. We can do a one-sample t-test. And so first we have we can just plot the data here. So here we have this, again, we're looking at this moon-planet relative diameter. So we're going to see if the value here is significantly different from the mean here. It should be, right? But let's just check. So the population mean of moon to planet diameters here is about 0.018. And we know that the moon is an outlier, so we're going to not include that in the mean. So we can use this one sample t-test function from SciPy to test whether that moon-planet distribution with no outliers is different from, say, a value of 0.02, which would be right around here, which is close to the mean. So this p-value is not significant with, say, an alpha of 0.05. So we cannot reject the null hypothesis that the mean is equal to the population mean. However, if we do that same test with 0.273, which is this value over here of the moon, we get a highly significant, very small p-value, which says very clearly that this value here could not be the mean of this distribution. If we have a two-sample t-test, we can also compute that to test whether two independent samples have the same average. So in this case, we're going to create two random distributions, A and B. And these are both going to have centered at 0, except this one will actually be centered at 2. So A is centered at 0 and B is centered at 2 with a normal distribution. So those should have different means if we're doing it right. So we're going to do a there's several different ways to do this. We can use the SciPy functions under stats, t-tests, ind. We give A, B, and then there is an option here for equal variance. This is actually true. I'd done an example before where these were not the same, but these should have the same variance. So those are true. Actually, don't change that. Change that back. I changed this in one example, but let me do this. So I'm going to change so they have a different variance. So A and B now, because I've made the spread of B wider, they now have a different variance. So let's rerun that cell, and now we're going to compute the t-statistic and the p-value using this stats t-test independent, and the p-value is highly significant. So according to this two-sample t-test, the means are different, which is what we expected. A second way we can compute the two-sample t-test is to compute the stats individually and then combine. So rather than computing the t-test based on the raw data, we're first going to calculate the mean, the variance, the sample size, and the degrees of freedom, and then compute the two-sample t-test from those statistics. So it gets us the same exact answer. It's just a different way. It's a way where we can see more what's going on with the data. So here we're going to calculate all these statistics, feed those into this function t-test ind from stats. We pass the stats, and then we can see we get the same answer. A third way we can compute the two-sample t-test is using the formulas directly. So here we're using the formulas that are used to compute these different statistics, and then evaluating it based on that, based on the t-statistic and the p-value. So the f here is just t from the formula and p from the formula. So different ways to get the same thing. And if we now look at the dist plot using Seaborn, we can see that we have, again, we can see that these distributions are different, and it makes sense that they're statistically distinguishable using the two-sample t-test. So if we have more than two groups, we can do an Anova, which is so the two-sample t-test is a special case of an Anova where you only have two groups. But if you have more groups, you can run an Anova, again using SciPy. And it assumes that the samples are independent, that the samples come from a normally distributed population, and that the standard deviations of the groups are equal, which is known as homoskedasticity. So if these assumptions are not true, you may be able to do a Kruskal-Wallis test, which is this function Kruskal, but I won't cover that today. So the example here is using some mussels from different parts of the world, and so here we're just looking at a subset of the data. So we'll just load that data, and then we're going to generate these dist plots. So we can see it looks like we've got 1, 2, 3 different kind of clusters of data here. So by eye, it looks like the Anova should tell us that these means are not all the same. But let's run that test. So we can simply run scipy.stats.f one way on these 5 populations, and it gives us the Anova statistic and the p-value, which is highly significant. So we get the F statistic of 7.12 and P of 2.8 times 10 to the minus 4th. And we can also compute some other statistics here, but just with this simple example, we can reject this null hypothesis that these 5 populations have the same mean. Okay, so this is just some introduction to SciPy and using this to do things like ANOVAs and tests of independence and t-tests and things like that.